Exercise 3.11. Let A be a subspace of a topological space X and D a subset of A. By int AD and int XD, we mean respectively the interior of D in the subspace topology on A and the interior of D in the topology on X. So part A, we're supposed to explore the relationship between int AD and A intersect int XD. And what that means is for each containment, either prove that it holds or find a counterexample. Okay. So you can look at the picture up here. We're first of all thinking about the interior of D as a subset of A here, with the subspace topology from X. And then we're looking at the interior of D as a subset of this large space X, and then intersecting that with the subset A. Okay. It seems plausible these could be the same, but they actually aren't. One of them could be smaller than the other. Okay. But let's first of all prove the containment that does hold. It turns out that this intersection is always a subset of int AD. And here's why. Since int XD is open in X, right? It's the largest open set contained in D. Therefore, it's certainly open. Well, then we have that A intersect int XD is open in A. And that's by the definition of the subspace topology on A. If you take an open set in X and intersect it with A, then you get an open set in A. All right. Well, since this intersection is also a subset of D, right? Int XD is certainly a subset of D, and so the intersection is as well. We have what we want, namely that this intersection is a subset of int AD. Okay. Why? Well, this intersection we said is open in A, and it's a subset of D, and int AD is the union of all open sets of A contained in D. Okay. So that union certainly contains this particular open set of A, which is contained in D. All right. So that inclusion holds, but the other one doesn't. And so maybe I can convince you of that by looking at the picture up here. If you think about the interior of D and A, it's going to contain everything on the inside of D, as you would expect. It's also going to contain these points from the boundary of A. Okay? Because if you sort of forget about X being here, those points are, they're not close to anything else in A, right? You can think of them as being in the interior of D. However, when you look at D as a subset of the large space X, these points here are no longer in the interior of D. Okay? So the interior of D in X is actually smaller than the interior of D in A. And there's no way that int AD could be a subset of this intersection. All right, so that's sort of a intuitive visual explanation, but to prove it, let's find an example that's maybe simpler than that picture I drew up there. Okay, so let me just say it's not necessarily true that int AD is a subset of the intersection. For example, we can let X equal about the real numbers, and let D and A both be, you can say, the closed interval from 0 to 1. Okay. Well then, since D is open in A, right? D is equal to A, so it's actually open and closed in A, right? Since D is open in A, we have that its interior inside of A is just itself, right? It's already open, so its interior is itself. Well, if we look at the intersection here, we can figure out what it is, right? A is just closed interval from 0 to 1, and the interior of D, which is that same interval inside of the real numbers, well, we lose the endpoints, right? We just get the open interval from 0 to 1, and that intersection is equal to the open interval from 0 to 1. Okay, so we have the left side here is D, which is this closed interval from 0 to 1. The right side is the open interval from 0 to 1, which certainly does not contain D. Right? So we've shown that this containment here does not hold for this particular example. And that means we're done.